We're going to look at some R code now that would allow you to draw random samples from the various distributions that we've discussed in class. I say random samples. The reality is that whenever you ask a computer program to draw numbers randomly, it does not do so randomly. Computers use pseudo-random number generators. The sequence of numbers that will be generated will have a lot of the properties that you would expect to see from numbers that have been randomly generated, but they're generated with a seed, and the seed makes it so that you can replicate the samples, which means that they cannot actually be taken randomly. So they'll behave randomly, roughly speaking, but they are not actual random samplers. How would you draw a value from a random uniform distribution? The function of interest in R is called RUnif, random UNIF. UNIF is the short form for the name of the actual uniform distribution function in R. If you query the help file, it will tell you that there's actually 4 different functions that are related to uniform distribution. I'll use the R version of that one just to give you an idea as to what it might look like. In the slides, you will also see we use PUnif. So if you want to draw a sample of size 1 from the standard uniform distribution, the one on the interval 0, 1, you just run unif 1. So the 1 here tells you the number of numbers you're trying to pick. In this version I got 6934059. Because I hadn't set the seed, if I run it again, I am going to get a different number. Now, let's say that I actually set the seed. You set it as 1, 2, 3, 4, just for the purposes of this experiment. So now it is assuming that my random number generating function will be seeded by this number. So every time I run any call to a random generation, I should be getting the same number. So if I reset the seed and I run, sure enough, I get the same number. If I run it the second time, I am not going to get the same number because now the seed has been set 2 iterations ago. Every sequence of random number calls will be the same based on this seed. You could generate more than 1 random number. Here we'll generate 10 of them. I'll assign them to an object called X, but I'll display them. Here are 10 randomly generated uniform numbers between 0 and 1. And if you want to see what they look like, draw a little histogram here. Doesn't look very uniform, but keep in mind we've only selected 10. If you wanted to do it with 100 numbers, more of them, and if you look at the histogram now, that's starting to look a little bit more uniform. Still some drops, but that's going to happen. If I increase the number of breaks equal, we get what we would expect to see. Some movement, but again, that's normal because we have 1 sample from a distribution. There's going to be some blocks with a few more values than other blocks. We can compare what the mean value of this block would be compared to what we would expect it to be. My mean is 0.4. You would expect the mean to be 0.5. I'm close. The variance now, we would expect it to be about 8.3% or 0.083, and we're seeing 0.07. Not bad. If you wanted to generate, I should say, numbers that do not come from the standard uniform distribution, the 0, 1 distribution, well, you'd have to set your limits. Here I'm going to randomly generate 250 numbers from a distribution which is uniform on the interval -2 and 3. Generate them here, and we'll look at the histogram. Sure enough, get something which is uniformly distributed, but you see now that the values range from -2 to 3. And if you were looking at a different set of breaks, here we'll break by 0.1 interval, get more breaks. Again, it looks fairly uniform. Some ups, some downs, completely within the realm of what you would expect. If you're interested in normal distribution instead, well, you're not going to be using the RUnif function. You're going to be using the R and whatever the shorthand for the normal distribution is. In R, it's called norm. So rnorm 1 gives you what you're looking for. If you run the help function here, you will see help file on the normal distribution. dnorm, dnorm, qnorm, rnorm, and so forth. So you can draw 1 number. Here's 1 number. You say it's negative. It's close to 0, as one would expect from Well, when you sample from the standard normal distribution, if you don't specify any parameters, it assumes that you're generating numbers from the standard normal. The normal would mean 0 and the standard deviation of 1. So let's generate 500 of these. Those guys, we'll plot the histogram. Now remember, when I just assigned the computation, nothing shows up here because I haven't displayed it. I don't really want to display 500 random numbers. That is not super useful to see, but if you plot the histogram, you will see something that looks like a normal distribution. Some movement, some noise, but it certainly has most of its weight around 0 and then tails that decrease. You can change the number of bins. This piece of code, for instance, I am creating 20 bins between the minimum value in my sample and the maximum value in my sample. Doing it this way, I see that some of the bins are empty. That might happen. Now, when you run yours, if you don't run it in the same order as I've done it, or if you've set a different seed, you will get a different histogram. You will have obtained a different sample of 500 terms. If you want a distribution which has a different mean and different standard deviation, you go and you specify what you want. Here I'm going to pick 5,000 observations from a normal distribution with mean -2 and standard deviation 3, and we'll look at the histogram later, but to start with, if we compute the mean of our normally distributed samples, we should be getting something which is close to -2. Sure enough, I get -1.98. That's pretty close. And if I look at the standard deviation of my sample, it should approach the standard deviation of the true population that it came from. 3, yeah, 2.97 is very close to 3. Well, that's pretty good. And we'll make a histogram here with 50 breaks, and we get the histogram. You can see that it does have the kind of shape I would expect from a normal distribution. Well, you won't be surprised that you can get the same type of thing for all of the other distributions. For instance, if I'm suggesting that you run the following, what do you think is going to happen? You are going to be generating 500 numbers from a Poisson distribution with parameter lambda 13. Well, what are the values of u? Here you're noticing something different. I'm only ever generating integers, because a Poisson distribution is a discrete distribution on integers, counts. You can compute the mean. The sample should be close to 13. That's good news. You should compute the variance. Should also be close to 13, because in a Poisson distribution, the mean and the variance are supposed to be the same. So in a sample, the mean value, the empirical mean value, and the empirical variance should be approximately equal. If you draw the histogram, or if you plot the histogram, for this specific sample, I have something that looks like this. So you see, this isn't a normal distribution. It is skewed, definitely. What do you think this piece of code will do? You are sampling 1,000 values from a binomial distribution where the number of the trial is 11. That's the name of the parameter. And our binom and the probability of success is 0.2. You would expect this to look like a binomial distribution, and it sort of does. Now, the number of breaks that I'm using isn't ideal here. You see there's a bunch of empty bins. Much better to generate a number of bins which would just be the integers between the minimum value and the maximum value of the number of successes. If I rerun this histogram, yeah, I get something that looks like what I would expect it to look like. I could try a different binomial distribution with different parameters. Here we'll use an n of 19 and a p of 0.7. We just rerun our little bit of code for the breaks, and we get a different shape. Again, when n increases, the binomial distribution ends up being close to a Poisson distribution, which ends up being close to a normal distribution with various parameters. You can find the exponential distribution as well. You won't be surprised to find out that it is Rexp that gives you a sample of exponentially distributed values. 1,000 samples will be selected. What about this 100 here? Well, this 100 is the parameter of the exponential distribution. And if you are not sure what the parameter should be, and I often get confused myself, I have so many functions, you go there and you'll find it's the rate parameter. Work out specifically what R has in mind for this by reading the documentation. If we look at the histogram here, we see something which is exponentially distributed. That makes sense. R gamma would give you a gamma distribution. If you're interested in other types of distributions like the joint normal, I'm going to show you some code on the notebook that allows you to do that. I won't run it here on the screen, but just be aware that this is the kind of work that you can do with R. I don't know if you remember, we saw some example about scheduling night shifts in the maternity ward of a hospital. At some point in the process, we were computing Poisson values, Poisson counts. Well, here's how you might do the same work in R. In the example, the average number of deliveries per night was about 1,000 divided by the number of days in a year. And that gave us a value of about 2.74. So let's assume here that our lambda parameter is going to be 2.74. We'll look at the number of births or deliveries we can have each night. That number could go to infinity, but you can't plot to infinity on a piece of software. So we'll just look at what happens between 0 and 10. I'm going to call different functions here. I'm not calling R Poisson and P Poisson. I'm calling D Poisson and P Poisson. D Poisson, D and whatever random distribution you're interested in will compute the probability mass function for the various values of X. And P Poisson will compute the cumulative mass function. So now let me just run all of those, and what you should see when I combine all of these into a data frame is the probability of obtaining exactly 0 deliveries, 1 delivery, 2, all the way up to 10 in the Y column, and the cumulative probability of obtaining 0 or fewer deliveries, 1 or fewer, 2 or fewer, 3 or fewer, all the way up to 10 or fewer. I stopped at 10 here because, well, I will never get exactly 100%. Because the Poisson distribution does go to infinity, but 99.98%, 99.99% if you do the roundup, that sounds like a good place to stop. And if you wanted to perhaps plot the distribution itself, you might consider doing this. This is the probability mass function that corresponds to these values of y that we found here. And if you wanted to plot a cumulative mass function, you might consider the following code. Now, if the ward wants to prepare for the greatest possible traffic on 80% of the nights, how many deliveries should be expected? You're looking for the number of delivery which will sandwich 0.80. It's much easier to get a sense of the problem if we do a visual display. The line y equals 80% crosses the CMF at x equals 4. Let's take a look at what the probability is for 3 or fewer deliveries and 4 and fewer deliveries to confirm that sure enough that's the number that we want. In our Poisson distribution with parameter lambda equals 2.74, what's the probability cumulative that we will see 3 or fewer events? It is 70%. And what's the probability that we will see 4 or fewer events? 85%. So if the hospital prepares for 4 deliveries a night, they'll be ready for the worst on at least 80% of the nights. Well, they'll be ready for the worst on 85.7% of the nights, but at least 80% of the nights. This is not the same question as asking how many deliveries are expected nightly. Because nightly you expect 2.74 deliveries on average. That's the lambda parameter. That's the expectation of a Poisson distribution. 85% of the time, 86% of the time, you would expect there to be 4 or fewer deliveries. or up to 4 deliveries. On how many nights of the year would you expect 5 or more deliveries? Well, you need to evaluate the probability that X is greater than or equal to 5 on any given night and multiply that by the number of days in a year. Now, I'm using a standardized number of days here, 365.25, because there might be some leap years in the process. About 52 days. About 14% of the nights would see 5 or more deliveries. Now, over the course of 1 year, what's the greatest number of deliveries you would expect on any night? You're looking for the largest value of X, for which the number of days times the probability of seeing that number of delivery, X, would be greater than 1. Because if it's not greater than 1, then the probability of that number of deliveries occurring during a year is too low. You wouldn't expect to see it. Here's a little bit of code that would do this for you. Again, we're going to re-specify the lambda in question, although we don't really need to re-specify it on account of it's already been initialized before. We'll set up a quantity that computes the expectation over a year for each of the number of deliveries between 0 and 10. And so we're seeing here that there should be about 23.5 nights with no deliveries, about 64.5 nights with 1, 88.5 with 2, 81 with 3, 55 with 4, 30 with 5, 13 nights, or 14 nights with 6 deliveries, about 5 nights with 7, about 2 nights with 8, about 1 with 9, and on average, no nights with 10 deliveries. To find the largest index for which this happens, you would find that it is indexed number 8. To say, you look at the actual probability alone here separately. To go to the other one, the expected number would be smaller than 0. It rounds up to 1, but it is still smaller. So the most you would expect in any given year would be 8.